This video will explain the rules for predicate logic in our system. So we're going to have 4 rules in our system. The first is the rule of universal formula out, which we will abbreviate with the upside down A, or the for all sign, and a capital O. Then we have the rule of existential formula out, which we will abbreviate with the backwards E, their exists symbol, and a capital O. And then the third rule is the rule of existential formula in. And we'll abbreviate that with the backwards E and a capital I. So I will now explain each of these rules before explaining the fourth rule that we will have. So first I will explain the rule of universal formula in. So that says that if we have the formula for all x, if px, then qx, well, from that we can derive the formula PA arrow QA. And we can use any of the letters A through V to what's called instantiate the universal formula. It's called instantiating because we're creating an instance of that formula. And that's the rule of for all out. The rule of existential formula out lets us instantiate existential formulas. So if that we have the formula, there exists an x such that px and qx then from that we can derive the formula PA and QA by the rule of existential out. And we want to flag that we use the letter A here. Because while, like with the rule of universal out, we can use any of the letters A through V, there is a restriction on existential out. Which says that the letter we use to instantiate it, so let's say A in this case, must be new to the proof. So that means there can't be any A's in any of the premises, or in the conclusion, or in, any previously derived line. It doesn't matter if it's in any line after it, but it can't be in any previously derived line. So I'm going to show why we need such a restriction by looking at a proof of an argument that's invalid, but which we would, if we didn't have that restriction, we would be able to prove that conclusion. So consider the argument, some kangaroos can fly. So there exists an x such that x is a kangaroo and x can fly. And then let's suppose we also have the premise that Karen is a kangaroo. And then suppose we tried to prove the conclusion that Karen can fly. Now this conclusion is invalid. This argument is invalid because it could be true that there are flying kangaroos, and it could be true that Karen is a kangaroo, but it still could be false that she could fly because she's not. It could be the case that she's not one of the flying kangaroos. So if we have the restriction on the instantiation of the existential formula, then we can't use K. We can't say KK and FK by one existential out, because we've already used K in our argument. So it keeps us from being able to say KK, and that keeps us from being able to assume that Karn is in fact one of those flying kangaroos. Because if we could do that, then we could very easily get to our conclusion. But we can't do this. So instead we have to do something. We have to say, let's use A, because A does not break the restrictions, because it does not already appear in the proof. So there's no problem with using A. But that won't help us get to our conclusion. So we will not be able to do a proof of this argument, which is good because this is an invalid argument. Okay. Then we need to look at the rule of existential formula in. And that says that, well, if we have the formula PA and QA, from that we can derive that there exists an X such that it has the qualities P and the quality Q by existential introduction. Okay, now the last rule that I need to introduce, you might think that the next rule that I'm going to introduce is a rule of universal formula in. Because after all, so far we have universal formula out, existential formula out, and existential formula in. So if we were following the usual pattern for our rule set, where we have an in and an out rule for each operator, then it seems like we should have a rule for all in. However, we're not going to have that, because like existential out, the rule of for all in would have a number of restrictions. It would have even more complicated restrictions than there exists out has. So we're just going to skip that. And we're going to work around this by every time we want to derive a universal formula, we're going to do so via reductio. We're going to do so by assuming the opposite. So if we want to prove for all x, if px, then qx, we will assume that that's false, and then try to get a contradiction. So I talk about that extensively in my video on universal formula reductio strategy. So you can go there and you can learn all about that. So that's not the fourth rule that we're going to need. The fourth rule that we need is the rule of quantifier exchange. We abbreviate that with the initials QE. And how this rule works is if we have, let's say, a negated universal formula. So let's say this is the statement, not all things are poisonous. Well, what does it mean to say it's false that everything is poisonous? Well, that's to say that there's at least one thing that's not poisonous, because otherwise everything would be poisonous. Likewise, we can have a negated existential. So if we say, it's false that some things are poisonous. Well, what it means to say it's false that some things are poisonous is to say nothing is poisonous. So for every X, X is not poisonous. So we can use these equivalencies in order to get rid of negations on the outside of formulas. Because as I said, whenever we want to prove a universal formula, we're going to need to assume its opposite. But then we can't use any of our other rules. We can't use any of our other quantifier rules on this because the major operator is not the universal quantifier, it's the negation. And we don't have rules that let us, then instantiate this if it has a negation on the outside. So we need to be able to move the negation in. So the rule of quantifier exchange lets us do that. So from it's false that for all x, if px, then qx, what we will get by quantifier exchange is there exists an x such that it's false that if px, then qx by quantifier exchange. So I'm going to show how the rules of universal out, existential out, and existential in work in the context of a proof. We're not going to use quantifier exchange in this proof because we don't need it in this particular proof. If you want to see how quantifier exchange works in action, go watch the video on the universal formula reductio strategy because that's one of the main places where using quantifier exchange comes into play. Okay, so here we want to prove an existential formula. There exists an x such that Rx and not Qx. So we're going to get this by the rule of existential introduction. And to do that, we need a formula of the form Ra and not Qa. And then we can do existential in. In order to get Ra and not Qa, we need to instantiate lines 1 and 2 using universal out and existential out, respectively. And then we can use the rules of propositional logic in order to get the resulting formulas to derive Ra and not Qa from those formulas. So now we have a universal statement and an existential statement we need to instantiate. And, in theory, it doesn't matter which we do first. However, in practice, we always want, in other words, it would be valid to do right away, line 3, instantiate line 1. That would be perfectly valid. The problem is that if we do that, so if we instantiate the universal formula first, then when we go to instantiate the existential, we can't use A because we've already used A on line 3. So we'd have to use some other letter, let's say PB and not QB by 2 existential out. We'll flag B. But then these formulas won't be able to, the formulas on line 3 and 4 won't be able to be used together to get what we want, which is RA and not QA. So if instead we do the existential formula first, it's going to work a lot better. So if instead we say PA and not QA by 2 existential out, and here we're going to flag A, and here it's fine to use A because A has not already occurred. And then we can use A again by doing the universal formula because there's no restrictions on universal formulas. So we'll do 1 for all out. And now it's a matter of using the rules of propositional logic to get RA and not QA. We can see that that's a fairly simple proof. First, we want to get PA out of line 3 by 3 and out. Then we can use that PA and the PA arrow RA to get RA by 4, 5, arrow out. And so now we have half of what we want, the RA and not QA. So we just need to get not QA, and that's easily done by 3 and out. Then we put those together by 6, 7, and in. And then we're ready to do our existential in step. So that will be by line 8, so that's line 9. And our proof is complete.